Yeah. So first, let me ask. Are there any questions, or how was the speed in the morning? Is that too fast or too slow, or Is okay or okay? Yeah. If you don't say that, I'll keep going faster. So that. Okay. All right. So. This morning we talked about production of things, right? Producing the cross sections. Of course, being produced doesn't mean that you can see them. Okay, so we need detectors to see those particles. So let's go over briefly what the collider experiment they can see, what kind of things they see. Okay, so the objects. Okay, what we call objects that we can see. Okay, the first is cluster of hadronic energy. Okay, we'll see a cluster of hadronic energy. So that's the kind of thing we can see. So it's some localized energy deposit in the detector. So these things, I'm sure many of you heard, is called a jet. Okay, and what give you jets? Okay, so at the fundamental level, there's quarks and gluons give you jets. Okay, so you all learn this. So a quark going through, it will radiate. The radiate, and then make a lot of radiation and make a jet. And the formation of jet or property of a jet is a separate topic. It's a very big topic. Again, we can just do 3-hour lectures just on that, but I'm not going to get into it here. So if you see jet, it's mostly a proxy for these things. Okay, so in Feynman diagram, if your final state is this in the detector, it will be a jet. And there's something else you can give you a jet, which is a tau lepton. Okay, a tau will decay to a neutrino. Well, if you draw a diagram, you will say this is a very off-shell W, right? So, and this decays to QQ bar. Okay, but that's not a very good picture of thinking about it. Okay, a better picture is to just say the longitudinal part of the W mixed with pion. Okay, so this is essentially this actually gives you a pi. Okay, right? That's called a one prong. Okay, so the difference between this and that, and there are other ways to detect tau. Of course, W can do leptonic decays as well. Okay, so then there are other ways to detect tau, and this between this and that is that this one has a lots of hadronic activity. Okay, it radiates a lot, and this one only has a little bit, which is a pion. Pion is a strongly interacting particle, and so it does give you a bit of hadronic activity, but it's not as much as that. So this is called a narrow jet. This is a normal jet. Okay, this is one way of tagging taus. The second part of type of objects are called the leptons. Okay, so we are using the terminology of experimentalists. So for them, leptons, for us, leptons, for serious, the leptons means E mu tau and neutrinos. Okay, for them, leptons only means E and mu. Okay, when they say you have leptons, they mean E and mu. Okay, this is a charged leptons, charged light leptons. Okay, these things. Okay, 3, photon. Then there is something called a heavy flavor. Yeah, tau sometimes you can call it heavy flavor too, but for mostly this just means there's a bottom and a charm. Okay, you can distinguish them somewhat, not very well, but these two. Okay, they also give you hadronic energy. Okay, what they do is they give you jet. Okay, but because they also have a lifetime. Okay, well, everybody has a lifetime, but this guy has an interesting lifetime. Okay, tau of B is about 10 to the 12 second, where tau of c is 10 to the minus 13 second. Okay, they are not that different. Okay, this is just rough numbers. You can look it up. But what this does is that this is about 10 to the minus 4 meter. Okay, so it actually gives you a little bit of a displaced vertex. Okay, you can actually you can tag the decay product of B and go back and see that it's actually not decayed at the where it's getting produced. Okay, every event there's an interaction point, and you in the collider you can see that, and then you see a lot of things coming out, right? So this is in the collider, in the event you can identify something called interaction point. Right, but when there's a B quark, you will see that it has something like this, right? So you can tag this as a B. Okay, this is way super oversimplified version of how we do B tag. Okay, but this is one of the ways to do it. Okay, so there's some efficiency of tagging a B, and there's also a chance that a random. Okay, everything can fake everything else, but in this thing, there's a kind of fake. Sometimes can fake a B with a jet.
Those times are in the lab frame.
Huh?
Those times are in the lab.
This is in the center of mass frame. There's a gamma too. There's usually, yeah, you're right. There's a boost usually. When the B quark is, yeah. Yeah, I'm not actually completely. I don't remember the number in front, but you can, I think you can look it up. Okay, and the neutrinos. Okay. Yeah, what's the signal of a neutrino? Yeah, you don't see it, right? Missing energy. That's right. So this is a cross section. This is the cross section of a detector, right? This is the direction of the beam, right? So let's say, imagine you're producing. If you're just producing neutrinos, we see nothing. Okay, these detectors are not nearly big enough to capture neutrinos. Okay, even you have a swimming pool there, you only capture a tiny fraction of neutrinos. So usually you don't see anything. Okay, but if you produce it together with something else, okay, these are visible things. I say these are visible. This is visible. Okay, any of these things, they can be visible, right? So. But when you see an event like something, visible coming here, visible going there, and then by momentum conservation, you derive there's something over there. Okay, or you're violating momentum conservation, which is actually quite interesting. But there's a conservative assumption is that there's something going over there. Okay, and the conservative assumption again is that this is actually a neutrino. Okay, not necessarily. Okay, there can be dark matter. Okay, now we finally talk about dark matter. This can be dark matter. Okay, that's also missing energy. But the conservative assumption is that it's just neutrino. Okay. So these are the things we can. So this is usually called the missing transverse energy, and or missing transverse momentum actually to be more precise. It's called the MAT sometimes, or ET, something like that, or PT. Actually, it depends on what you. Yeah. Okay, so these are the objects. But since we're talking object, let's just go over very quickly how do we actually identify these objects. Okay. Again, this is not an experimental lecture, so I'm going to be very sketchy about these. How do we actually do particle ID with the detectors? Okay, so I'm going to draw a super cartoon about the detector. Okay, actually I'm not going to draw a detector at all. So I'm just going to show you. There's a detector has multiple layers. So I'm going to draw you some layers. Okay, so let's say imagine this is a detector. Okay, my particles are coming this way through the detector. Okay, and so actual detector is a cylinder with multiple layers. Imagine I'm just taking a wedge out of it. Okay, so this is not to the scale, very not to the scale. Okay, And so the first layer is what we call tracking. There are many ways to do tracking, but you know, I'm not I'm not the right person to talk about the different techniques. But roughly speaking, to series, what it does is that it captures the tracks of charged particles. Okay, when charged particle goes through this layer, you see a track. Okay, so this is like a charged particles. And then the second layer is called the E and M calorimeter. Okay, well, sometimes called let me just call it eCal, electromagnetic calorimeter. So but the name implies that it measures the amount of energy. Okay, so the charged particle, again, anything has a electromagnetic interactions. Okay, anything has E and M interactions will deposit energy here in this layer. Okay, that's called eCal again. And the next layer is called HCal. So it's hadronic calorimeter. So usually, it's a much thicker and a dense layer than the eCal. Okay, so they, anything. So this is the hadrons. Hadrons actually deposit their energy here. Okay, the last thing is usually the biggest part, is the muon chamber. Okay, so the muons leaves tracks here. Okay, but just by the name of it. Okay, it's much bigger because muon is very heavy, much heavier than the electron. For magnetic field we usually have, it bends with a much bigger curvature than the electron. So in order to measure the muon momentum and its charge, you need a much more space. So that's so I don't know. Have you seen the size of the detector? It's a couple story high, building high, and the most of the volume is muon. So this is the biggest part. Okay. And this is actually very small. The first one is very small in the middle. Yeah. Okay. So now let's think about what does those guys do? When they go through, right? So let's think about if it's E plus E minus going through this, right? So it's going to leave a track here, right? And it's going to deposit its energy here. Okay, that's what the electron look like. Okay, very sketchy. Okay, so a photon going through. Okay, you see nothing here. Okay, and you see energy deposit here. That's what the photon going through. A muon is leaving a track here, and the muon, because it's heavy, it does not deposit that much energy actually in the eCal. Okay, so basically they deposit energy because they Bremsstrahlung, but Bremsstrahlung is down by a fairly large power of mass. So the muon doesn't quite deposit energy here, and it actually bends here. Okay, so so muon go all the way through. Okay. And now if you have hadrons such as pions or protons and so on, okay, charged pions and protons, and leaves energy here, leave a track here. That's a charged hadron, and doesn't do much here because the material is not dense enough to stop it, and it leaves its energy here. Okay, and if you have a neutron, for example, it doesn't do anything here. It just deposit energy here. Okay, so but these are all part of a jet. Okay, usually you identifying just a pion or proton is not very useful because you cannot really quite calculate from QCD, the number of pions you have, a particular pion momentum, so on. These are not quite calculable. Okay, so these are basically the way we actually identify objects. Okay, so again, this is a very cartoon version of the what's so-called particle ID. Yeah. Of course, it's not never as clean cut as this. Okay, anything can fake anything else. Okay, but that's the rough category. Okay. Now with this, let's go over some of the standard model processes. Okay. So in order to make discoveries, first we have to understand what's already known. Okay. So let's understand some of the standard model process. Let's see. Well, where is the? Oh, let's see. Well, going through all of them is certainly is going to take a long time. I'm not going to do that, I'm just going to let's just look at a few of the important ones. Okay. So this is a PP to X, where X equals to, for example, it can be dijet. Okay, this is just the production of two jets. Okay, the production of two jets. If I don't have any cuts, the cross section is infinite, not infinite, but it's very big. Okay, but that's also not very useful, because what actually counts for the background of the standard model is usually very hard jets. So let's give it a cut. Okay, PT greater than 250 GeV. Okay, remember PT is a good observable, good kinematical variable to think about. So this is not that's not necessarily the only cut you can put. Okay, that's just to guide your eyes. Okay, so. And that cross section is at 100 nanobar. Okay. So this is a huge cross section. Okay. Just for calibration, our luminosity is what? Luminosity right now is tens of inverse femtobar. Okay. And this is nano. Okay. There are, what is it? Nano, pico, femto. There are, hundreds of millions of digest events, at least, with this energy. Okay, maybe I think, yeah. Okay, 30, yeah. So more than a billion already. Yeah. So lots of these things. Okay. Then you can also have W. You can have a W production. Okay, this is a 2-to-1 production, onshore production of W. Okay. Do I need to draw the diagrams for this? And do you know the diagram that produces a W? Is it okay? I say something, otherwise
Yes.
W. Okay. Just in case you're wondering. Okay, it's not. I'm sure you have seen this before. I'm just to make sure. Okay, but W goes to leptons. Okay, this is sometimes okay, and this is 20 nanobar. Okay, it's also a very big cross section. Okay. And the Z to L plus L minus. Okay, that's also 2-to-1, and so it's a very similar cross section thing like this, and but this is 2 nanobar. Okay, it's smaller, mostly because the lepton has a smaller branching ratio. Okay, W to lepton is 20%. The Z to lepton is 5%. Remember, I am by lepton I mean E and mu. Okay, so and TT bar. Okay, the production of top quarks. Okay, it's about so this is all for 14 TeV. And it's very rough number. Okay, I don't blame me if I haven't been very careful of including next law or next leading order corrections and so on. None of these. Okay, I'm just this is just some rough number. 900. Okay, but now we're switching unit to picobar. Okay, it's almost a nanobar. Okay. And Higgs. Okay. Production of Higgs. What is the dominant mode to produce Higgs? Gluon fusion. Yeah, I think Christoph talked about this morning. I guess that's the diagram. Yeah, he drew the diagram already. Yeah. So that's this, And that is 30 picobarn, roughly. I'm not sure this is an n cube next leading order or not, but this is around that number, okay? And then WW, so I can, instead of producing 1 W, imagine I'm producing 2 Ws. Now I'm going to produce 2 W. Also from QQ bar initial state, okay, from producing 2 Ws. And this is 100 picobarn. Okay. All right. You see, there's some kind of hierarchy, right? Depends on whether it's one thing or two things, or if it's a QCD process versus weak process. So next, what I wanted to do is let's roughly understand the sum of these numbers. Okay, this is a good exercise for you to actually understand these numbers without actually doing your simulation. Okay, so at least you can try to understand something about the relative strength of these numbers, relative size of those numbers. Okay, so let me just remind you that the guidance we have, right, for this morning. So the kind of things we know, what the cross section depends on, right? So the first thing is depends on PDF or parton luminosity, right? That's one thing that depends on. So it depends on what the initial state is, and also depends on where the energy is. Okay, what is the parton fraction I need to worry about. Okay, and B depends on couplings. Okay, depends on whether it's weak coupling or strong coupling. Okay, depends on it's a QCD coupling or electroweak coupling. And then there's a depends on number of particles. Okay, we haven't quite done that yet, but there's a one body. But here is already one body. There's some one body process. There are two body processes. Okay, so adding each particle. You would have to pay some weak coupling. You have to pay some coupling constant. You also have to pay a more phase space. Right? This morning, at least we see the example of a two body versus 3 body. Okay, you pay something extra from the phase space. You pay some factor of pi's and so on, right? And also 3 body opens slower than the 2 body and so on. But roughly speaking, this is you pay by a factor of 10 to the minus 2 to 10 to the minus 3, adding one more particles. Okay, so let's just based on this see whether we can understand some of these. Okay, this thing keeps trying to come off. All right. Okay. Okay. First, let's understand the TT bar versus WW. Okay, so TT bar versus WW. So you can do some of this yourself, but I'm just going to sketch it. Okay, so it's a 2 body versus 2 body, so the phase space factor is similar. Okay, at least we don't have to worry about that. And but there is a PDF difference. Okay, there's a PDF difference. So let me actually draw something. TT bar. How is TT bar produced? Any diagram? What is the initial state? Many possibilities. Which one is the dominant one? Glue, right? So, for example, okay, this is of course you have more than that. You have like things like this, right? But you also have this, right? And this is much bigger than that. Okay, why? Because first of all, the number of coupling is the same. The order in terms of QCD coupling is the same. It's also 2 body, but this guy has more color than the other one. Okay, just because gluon has more color than quark. Okay, and that's not the biggest factor. Biggest factor is that the glue PDF, glue has more support than QQ bar at the TT bar energy. TT bar is energy threshold is 350. The center of mass energy is 14 TeV, right? So the you know, if you want the x1 times times x2 is less than 0.1. Okay, that's smaller fraction. So that's the regime where glue dominates. And so this is glue, but this is a QQ bar. Okay, and there's a slightly so that the glue is bigger than QQ bar normally, but there's a difference here. The center of mass of this is 160. The center of mass of that is 350. Okay, on the threshold. And if you look it up, well, and on the parton luminosity, the PDF at the 160 for QQ bar is roughly the same of the glue at the 350. Okay, and the roughly same. Glue at the 350 is slightly less than QQ bar at the 160. Okay, so again, I think I'll put this online, and so that I have a actual plot of parton luminosity, so you can do this yourself. But there's a coupling, and this is alpha s square. Okay. So this is a GS, and you square it. It's alpha s square. Okay, and this is alpha weak square. Okay, and it turns out numerically alpha s square is about 10 times alpha weak square. Okay. Yeah. So let's see. Yeah, so this is somewhat smaller than this, but this, well, this one is bigger than, about 10 times bigger than that, okay? But that's roughly, you see that roughly the cross-section here is about a factor of 10. Okay. Again, this way, I'm not claiming I'm going to understand better than a factor of 10, okay? But this is but you see that roughly speaking, it's almost completely coming from here, that factor of 10. Okay. So now, let's do something else, okay? Let's do the production of W versus production of H. Okay, the Higgs versus the single W production. Okay, the PDF. W is from QQ bar, H is from glue. Okay. And then there's a coupling. Okay. This is again alpha weak. This is alpha weak. Okay. So this is just again the diagram of this is just this. Okay. This is the diagram. Okay. So you have a G weak here, you squared. It's alpha weak. Okay. The diagram of this is this. Okay. What is this? This is a GS square, and you square it. This is alpha s square, right? Okay. Oh, or if you want, I can write GS. Okay. After I just wanted to understand the relative size. Okay. Like, let me write G weak square if you want. Okay. And then there's a loop. Okay. what's the size of this loop? I think, well, Christoph talked about this morning, if you look at his formula. But I cannot calculate loops, so I would just say it's 16 pi square. Okay. At least the number of pi's are correct. Okay, I don't know about the number of other things. Okay. Okay. So that's the size of this. Okay. And yeah, the mass threshold has a big slight effect too. So this is 80 GeV, and this is 125. And those are slightly different. Okay. So it turns out the glue at 125 is about 5 times QQ bar. 5 times QQ bar at 80. Okay, so it's a small factor. And G weak square is about I don't know. Let's just call it 10 to the 4th. 1 over 16 pi square. Square G S to the 4th. Okay. So these two factors, there is a 4 order magnitude difference, roughly speaking. Okay, there's slightly more than that. Okay, slightly more than that. Okay. Yeah. So if you put this together, you can understand the difference between between these and that, basically. Okay. This is I haven't taken into account the branching ratio yet. So you're supposed to multiply this number by 5. That's the inclusive W cross section, and this is the Higgs cross section. Okay. Roughly speaking, again, modulo a factor of few. Okay. So perhaps let me just comment on the one more thing. One more thing. So, the last thing, let's try to, again, I'm not going to do this in detail, but we can compare the dijet and the TT bar. Okay, we can try to do that, and you see that there's a 2 order magnitude difference between these two. Okay, and they all two body. They're all from glue. Okay, the only thing is that if anything, it's the other way around, right? The center of mass here is at least 500. Okay, because I need to have a 2 jets with greater than 250, so the energy is at least 500, and the energy here is 350. Okay, if you anything that hurts this process, because if you have higher energy, you have smaller PDF. But why is that a 2 order magnitude bigger than that? It's because this guy has many more diagrams than this guy. Okay, so for TT bar, as the diagram when we draw it, are roughly it's like this. Right, this is for TT bar. Okay, or you can include this too. Okay, you can include this too. Okay, so this is TT bar, but from QQ bar, from dijet, you have many more diagrams than this. Okay, and many more colors. Okay, there are more color factors too. You can have this. Right? You can have just the gluon diagrams. You see, there's already a lot. Okay, you can have all these diagrams, but you can also have quark diagrams, right? The gluon can produce quarks. You can have all these diagrams replacing top quark with a normal quark. These are all dijet. Okay, so there are just many more diagrams. Okay, and yeah, at least you get a factor of 20, 30 just coming from these diagrams. Okay. Depends on, so if they don't interfere, you just square them, add them up separately, and so on. So yeah, so it's not exactly the number of diagrams square, but it's something like that. Yeah. Okay, so now with this kind of argument, we can already try to think about what the kind of new physics we can have hope to see. Okay, so But well, let's. How should we do this? Yeah. So let's just get to it. Okay. So let's just by raw rates. Yeah. Okay. So already you see that if there's some new physics particle, that typically new physics particle, if they also have just give you 2 jet with 200 GeV, you each, it's almost hopeless. Okay, because this is huge. Okay, unless you have a okay, well we'll have to. So new physics has to have something new. Okay, has to have something new. There are 2 ways. There are 2 ways that the new physics can sort of win. Okay. There are basically 2 ways. Okay. One way is that there are 2 ways of 2 ways for discovery. One way is that if you have a standard model, so standard model always look like this. There's some distribution. Okay, there's an implied. I'm not going to even specify any of what distribution this is. All the distribution look like this. Okay, it's actually all the background of anything looks like this. I don't know. If you look at the cosmic rays, the background also look like this. So it's at some cartoon level. Okay, so there are 2 ways. One way is that if the new physics give you a very sharp feature on whatever that distribution is. Okay, where standard model don't. Okay, suppose you have a sharp feature. Like this. Then you say, okay, there's no way standard model can make this. Okay, so after all, yeah. Anyway, after all, we have a standard model Lagrangian, we can calculate and so on, and there's something here, right? Especially this happens at the energy scale much higher than any standard model massive particles. Okay, then after that, the standard model just have no scales, right? Standard model roughly at the TeV standard model is roughly a conformal theory, right? So there's no energy scales. Okay, so but if there's something, it's beyond some energy scale, I can make a feature like this. I think that's a way I can say there's no way standard model can give you that. Okay. Another way is that even though you don't have a very sharp feature, but somehow you look like this. Okay, you look like this, and at the very high energies, your rate is comparable with the standard model. Okay, so you have an access here, even though the feature is not so obvious. You have a feature here because because first of all you again the new physics is heavy, so you have to start out at some higher energy. But you have a little bit of access, and here is you have S around the same order as the background. So there you have a hope. Okay. Other than that, it's going to be very difficult. Okay. Yeah. So since I'm supposed to talk about dark matters, unfortunately, dark matter looks like this. Okay, that's why it's very difficult. Okay, well, we can get back to this, but dark matter looks like this. Okay. 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 So which one I should do first? Let's talk a little bit about the feature first, then I'll come back to do a little bit of discounting here. Okay. Let's talk about features, but features are. If you have features, it seems the life becomes good. Okay, very, very simple. Okay, so there are many kinematical features. So I'll just talk about the most obvious ones. Okay, the first is resonance. Yeah, I'm sure you have seen this already. Yeah, so this is X particle produced and it decays to A and B. Okay, this is okay, and there, what you do is that you say so if you consider the process like this, right? So you produce a particle and it decays to A and B. What you do is you say, I'm going to suppose these two are all these two are all visible. They are all visible. Okay, they are not missing energy. Okay, they are all visible. It means that you can measure its form momentum. So what you do is you just form the kinematical variable is just the S hat. Okay. So PA plus PB square. Okay, what is the S hat distribution for this? When you produce this, it's exactly this. Right. So it's because the propagator, the cross section is proportional to this propagator here, and then the propagator here is just the S hat minus mx square minus plus gamma x square mx square. Okay, so have you seen this before? This is called Bragg-Wigner form resonance. Okay, so there is it's in the so sometimes I can call this square root of S hat square root PA square PA plus PB square. I'm calling it MAB. I'm calling this invariant mass. Okay, it's Lorentz invariant. It has the function, has the dimension of mass. So if I make a MAB distribution of this, it looks like this. Okay, centers on mx, and this is the width of the particle. It's basically, or ideally, it tells you how broad this Gaussian is. Okay, in reality, for at least for many particles are very narrow, so you actually don't see its width. The actual width you see are just the resolution of measuring this momentum. That also will give you a width. Okay, so. Well, we can comment on that maybe later when we talk about the Higgs measurements if we get to it. Okay, but this is a very sharp feature. Okay, so the golden channel is QQ bar to some new particle decays to 2 leptons. So leptons are very clean. Okay, so then you do that. Okay, and that the name of the particle is called Z prime. Okay, all right. Yes, so for the C prime search has a rate reaches great because of this feature. So you basically you form an invariant mass distribution. You do bump hunting. That's called you just you either hunt by eye or these days you hunt by some neural net, and so you look for a bump. Okay. Now. The next thing we can talk about is what if you don't see one of the particles? Okay. Again, a typical example of this in the standard model is Z. Okay, Z decays to 2 leptons, but also Higgs. Higgs decay to 2 photons, or Higgs. No, yeah. So what are the examples? Maybe we can talk about it. So, no, it's Z goes to L plus L minus. Right, that's an example. Another example is a Higgs goes to gamma gamma. Okay. Right. Yet another example, perhaps this better example, is a Higgs goes to ZZ of shell goes to 4 leptons. Okay. Even though this is not 2 to 2, but you can add the momentum of these 4 leptons together. Okay. It also have a peak at H. Okay. So in 2012, or in 2012, it is this one that really convinced many people, even though this one has a much less event than this one. It's this one that convinced most of people that we actually have discovered Higgs. Okay, so that is anyway. Okay, so let's talk about if we actually miss a particle. Again, so a standard example, which let's just use that example, is a lepton plus neutrino. Yeah.
Why was the 4-lepton channel more convincing than the diphoton channel?
Because the photon is difficult. Photon is difficult. Yeah. We can talk about, I don't know whether, because photon has a lot of background. Okay. Photon has a, just give you a way to just give you a sense. So the Monte Carlo simulation for diphoton distribution has never agreed with experiment ever. Okay, so that is but because QCD can give you a pi zero also give you a photon, and that process is very hard to calculate and incorporate. So yeah, that's just in reality what experimental does. Experimentalists do for this guy is they say, okay, I'm not going to use any Monte Carlo. I'm not going to use any series predictions. I'm just going to measure the diphoton invariant mass. Okay, they measure it, and then they see a bump. Okay, and then yeah, but because you measure it, you could actually worry, is that any way that you calibrate the photon in such a way that you can actually make a bump, right? So I don't know. Does the number 750 means anything to you? And I think I'm wondering whether you're too young or not. But it's a well, that one is probably statistical fluctuation. But even at that point, people are already worried. Can any cuts or calibration? Suppose your calibration efficiency is actually mildly energy dependent. You can also make something like this, right? So. Okay, let's talk about W. Okay, so it's something like this. Now, okay, let's see. In order to consistent, let me call this momentum K1. Let me call this momentum K2. Okay, I'm just going to. Now you see that. So let's see what is the K1 distribution. Okay, but again, as I said, the K1 is not a very good variable. Okay, because it's not a Z boost invariant. What Z boost invariant is K1 perpendicular. Okay, transverse K1. So let's just ask what is the distribution? What is the distribution of K1 transverse? Okay, so yeah, let me just write a couple steps. Okay, so K1 T square is 1/4 okay. Again, all these guys has hats, so these are the parton center mass frame. But this is a Z boost invariant, so this means that I can calculate in any frame I want. Okay, so I'm going to calculate it in the parton center mass frame. For now, I'm in the frame where W is at rest. Okay, so then that's that. And from this, you see that the dk1 t square is okay, I'm just changing the variable to cosine, yes.
Sorry, what is theta hat?
It's the angle in the center of mass frame with respect to the beam direction.
Okay.
Yeah, even in my center mass frame, there's still beam still giving me a direction, right? So, okay. So then this is the Jacobian going from K1t to theta. The reason I wanted to go to this frame is that usually you calculate the cross section. It's a differential cross section with respect to cosine theta. Okay, in other words, this distribution is smooth. Okay, cross section in terms of this variable is smooth. Right? Usually there's unless you have some funny singularities, otherwise it's a smooth distribution of theta. On the other hand, this guy, well, again, homework is to verify this. Okay. And this guy has a singularity. Okay, when this is equal to that. Okay, and it has a shape. Okay, there's a particular shape. Okay, so this means that if you have a distribution of this, it's a smooth piece times this. Okay, of course the distribution will stop beyond the singularity, because there you violate you violate energy conservation. Okay, so and the kT is constrained to be less than half of the center of mass energy. Okay, so so if you this means that if you plot K1T, it would stop here. Okay, so this is a half of the center of mass energy. It will stop here. Okay, we cannot go further. Moreover, it almost diverges here. Okay, it diverges here, and moreover, it's it's going to this piece. It has this shape. It looks like this. Okay, so it looks like it looks like something like this. Okay. So this is also a fairly sharp feature. It's not as nice looking or symmetrical as the resonance, but there is a peak. Okay, and because it's coming from the Jacobian, it's called a Jacobian peak. Okay. Okay. So this is basically what you're looking for a W particle. Okay, so let me say a few more words about that. In reality, what you do is actually you're not doing the PT. Okay, you wanted to construct something that because I'm doing this picture essentially assuming that there's nothing else in the event. The W is along the Z direction, right? So then this is what I was doing from those calculations. Okay, but in reality, there may be some additional event at radiation in this. So you want to construct something that is also still has a peak, has an endpoint, right? So of that distribution, but it's relatively independent of whether you have additional radiation or not. Okay, so this is something called the transverse mass. Okay. So what you do is, let me write two quantities. Okay, first is the invariant mass. Okay. M12 square is E of electron plus E of neutrino square. Okay, minus K1T plus K2 T quantity square. Okay, so this is the transverse momentum vector square minus K1 Z plus K2 Z square. Okay, so this is just my definition, by definition of transverse invariant mass. Okay, I'm just taking the vector product of those two invariant. Okay, now I'm going to define some quantities. Let me define, well, this is not that useful. Okay, I'm going to call missing energy transverse energy, and that is just basically the momentum of neutrino. Okay, that's the missing momentum of neutrino. I'm going to define something else. It's the transverse energy of the electron. Okay, transverse energy of electron, which is basically the same as it's just the K1T, the magnitude of K1T. Okay, and I'm going to okay, anyway, the rest of it is not very useful. Yeah, I can also call this just the transverse energy of neutrino, basically. Okay, just different names. Okay, I'm going to define my MT square, my transverse mass. So this is my transverse mass, which is E nu T plus E nu T square. Okay, so instead of using E energy, I'm going to use the transverse energy. Okay, and minus K1T plus K2T square, and not including that. Okay. Okay. Now it's an exercise for you to show that this guy still has an endpoint. Okay. In the sense that you can show that M12 square is greater than MT square. Okay. And M12 square is just MW square. Okay, if you could W produced on the resonance, then this is just MW square. So therefore this guy still has an endpoint. Okay. Moreover, with if there's no radiation, no additional radiation, MT is approximately equals to 2 times K1T. Okay, if there's no additional radiation, you can show that this is true. Okay, this is going back to this case. It's just twice of the transverse momentum, the transverse mass. Therefore, the MT distribution also approximately have a Jacobian peak. Okay, just like the PT distribution over there. Okay, so let me draw that distribution. So now imagine this is MT. Okay, distribution. It has an endpoint at MW. Okay, but the endpoint is not it's not infinite. Okay, because this relation relies on this guy produced exactly on shell, but usually it's not exactly on shell. At least it's spread out by the width of the particle. Okay, so therefore this distribution will be something like this, right? So it will be something like this. Okay, and so the first thing is the endpoint smeared by the width Okay, but also by resolution. Okay, by the accuracy of you can actually measure this momentum. Okay, it will smear the endpoint too. Okay, and this shape here depends on radiation. It depends on additional radiation. Means that whether you have something like additional to that W or not. Okay, so the actual business of this is looking at this distribution is basically how we measure W mass at hadrons. But of course, it's not that simple. Actually, to actually do a good measurement, you actually need to predict this distribution very well. Now that really requires you calculate all these things. Okay, so it's a big business how to do W mass measurement accurately at hadron colliders. Okay. So, but the basic idea is doing this transverse variable. Okay, even if you have a, even you're missing half of the particles. Okay. Okay, so this is what I wanted to say about about the kinematical variables. But let's talk about the other case. Okay, the other case. Remember, we wanted to make discoveries when you actually have the S over B is around the 1. Okay, so that is if you don't have very sharp features like this. Okay, so those kind of scenarios are more relevant for things that you have multiple missing particles in the event, and you cannot really reconstruct any of the mass peaks very well. So a typical example of that is supersymmetry. Okay. Yeah.
When you say S over B to be equal to 1, what is that exactly for? Is that for a 5 using, and you can say potentially you could find it, or is that for
potentially you can find it, or potentially you can set a limit if you don't see it. I'm not distinguishing between 5 and 2 sigmas at this level, okay? But it's if you can do, yeah. So let's say S over B equal to 1. That's roughly speaking where you actually set the limit, or it's roughly speaking the same place where you can actually make a discovery. Okay.
Sorry, one question.
Yeah.
Regarding your physics, it only works for not stable particles. Or do we have some mediators like our W to get this sharp peak, to this Jacobian peak?
Yeah, if you have a W prime, it goes to L plus nu. Sorry, yeah, this is exactly how we do. What do we do to search for W prime? If you want, yeah. But you're partially right. This one is not too terribly useful in new physics searches unless you have a particle like a W prime. Okay. And and for fancier things, if you have like say sometimes you have 2 neutrinos, you have other things and so on. You can define some more elaborate version of transverse mass. Okay, there are many different names. Okay, but they share the feature that you want to construct in such a way that they have some endpoint, and near endpoint there's some feature. Okay, and but usually, this is the sharpest one. Okay, the more particles you're missing, the more things you involve, the things gets washed out pretty quickly. Okay. Yeah, so it becomes much less convincing than this. Okay. So a typical example of just doing things you can understand the reach by event. Just looking at where is the place where S over B equal to 1 is a supersymmetry. Okay. Have you guys all seen supersymmetry before? Very good. So the typical typical SUSY. So let me not repeat it, but let's just talk about the gluino search. Okay, just as an example. Okay, to understand this. Let's talk about gluino. Okay. But gluino has many ways of decaying, but let's just focus on one, simplest case. Okay, gluino goes to Q bar. Okay, there's some squark. It's on shell, off shell, doesn't matter. Okay, let me consider the case that this is off shell. So let's say the squark is very heavy. I don't see it. Okay, but you still have this decay, and this is LSP. Okay, LSP is typically some neutral superpartner which escape the detector. Okay, it's also our dark matter. Okay, that is. See, I'm talking about dark matter, the colliders after all, so all the time. Okay. Anyway, so this is but you also cannot just produce one of these, right? You usually produce two of them. Okay. So it's PP goes to gluino goes to jets plus mat. Right, so that's the channel that you look for. You look for jets plus missing energy. Okay, hard jets plus missing energy. And the limit, the current limit, is about 2 TeV on gluino. Okay, it depends on where you are, but roughly speaking, it's 2 TeV. Okay. Now, what is the standard model background? First of all, let's say for M gluino is 2 TeV. The rate is about femtobar. Okay. And this is easy. You take a matograph 1 second to calculate. Okay, less than 1 second. But let's see what is the standard model background. Also jets plus missing energy. Okay. So one thing is that I can have things like this. Okay, I can have jets. Okay, just add more gluon to it. Okay. Or I can have actually I can start with I can do this too, right? Okay, I can do this too, and this is new. So it can come from QQ bar, but it can also come from Q glue. Okay, that is but roughly speaking, both of this is what the rate is take a Z, add a jet. Okay, take a Z, add a jet, and the energy of the sum of these two guys. The sum of these two guys. Sorry, Jesus. Oh, what did I do? Yeah. And the sum of the energy together to be relevant for gluino search, right? Gluino has 2 TeV each, so the center of mass energy. So the center of mass energy here, the relevant center of mass energy here is 4 TeV. Okay, you are producing 2 gluinos. So the relevant energy here to qualify as a background of that guy. Okay, it has to be 4 TeV as well. Easy center of mass of this. Okay, so it's just a. Okay, so you can do this in multiple ways. Okay, you can estimate this background in multiple ways. You can just say I'm going to take a Z cross section, and I'm going to add multiple jets on top of it. Okay, just using some of our rough rules over there. Or I can also start from dijet. Then I'm going to add a Z to it. I'm going to add another jet to it. Okay, so that is that's another way of doing it. But so let's go with that route. Okay, so let's start with QCD dijet. Okay, that's 100 nanobar over there. Okay, so this is 100 nanobar over there. I'm going to scale the PDF. Okay, so the relevant energy here for the PDF is 500 GeV. Okay, we have 2 jet, each has 250 each. But this is from 500 to 4 TeV. Okay, I'm going to scale that. Okay, so that is you can look at the parton luminosity scaling. Okay, well, you don't have the figure, but if you look at the figure in my lecture notes, this is going to give you a factor of 10 to the minus 3. Okay, your rate will fall by a factor of 1,000. Just going from this to that. Okay. Now I'm going to add a Z. Okay, so I'm adding a particle, right? So my rule there is adding a particle. I get a 10 to the minus 2 to 10 to the minus 3. Okay. And now this is only 2 jets. Right, so this one usually has 3 or 4 jets. Okay, you don't necessarily have to see 4 jets. Okay, sometimes the jets gets missed, and sometimes jets sit on top of each other and so on. But it's let's say it's 3 or 4 jets. So at least I need to add another jet. Okay, at least I need to add another jet. And this is again adding another particle, so let's call it a 10 to the minus 2, okay? Or you can call it 10 to the minus 3 as well. It depends on what you want. You know, it's at this level, it's not very precise, but you see that this is enough to take this down to a femtobar level. Okay. Again, so you see that this is an example where the signal, the limit where I'm setting a signal is roughly the same order as the background. Okay. Again, this argument will not tell you the limit is 2 TeV rather than 2100 TeV. Okay, 2.1 TeV. But this does tell you that the limit cannot be 1 TeV or 1.5 TeV, as it cannot be 2.5 TeV either. Okay, because that rate is very different. Okay, so that's one of the examples to understand. You know, just you have to, you know, this question is very important. We cannot completely trust experimentalists. You have to, you know, verify it yourself. Okay, anytime you see a limit. So, okay, so that's sort of you in this way you sort of understand. It makes sense. Of course, detail difference. You know, there are many details to do an actual search. Okay, but at least 2 TeV is not crazy. Okay, you can do this. You can follow this route to do something else, right? There's another background so there are additional backgrounds. The background can be jet plus W. Okay, and where W goes to L nu. Okay, you say, okay, wait a minute, I have a lepton here. Okay, but lepton can get missed. Okay, lepton can, you know, be accidentally end up inside of a jet, or, you know, can miss the detector and so on. Okay, so you do pay a factor to actually to have to miss a lepton, but the W cross section is also adding a W. The cross section is greater than the Z cross section. So this can be an important background too. Okay, it's not detail which one is bigger, then depends on your cut. Okay, then it start to depend on your cut. And the TT bar is a background to this too. Okay, which is not too intuitive, but it is. You know, TT bar usually is a background for everybody. Yeah. So anything you wanted to do. So if you're wondering whether you have missed some background, just run TT bar. Okay. So it's usually it's a background. Okay. Okay, so let's just, you know, let's just look at you know how top quark decay is, right? top quark to B, and I think didn't Christoph calculate the top width this morning? I think to W, and the W decay can goes to lepton nu, and or can also goes to jets. So let's say I have this, okay. Okay. So the benefits of TT bar is that you actually, yes, it's a start out as a smaller cross section than dijet, but you start out having jets already. Okay, just by the decay, I don't have to add a particle. But by burst, it gives you a lot of particles already. Okay, you don't have to add a jet. And 1, 2, 3, 4 jets already. Okay, you say, wait a minute, I can tag B's. Yes, that's true, but you can only tag B's with certain efficiency. Okay, there's still a lot of order one fraction of the event that you don't actually tag this as a B, for whatever reason. You just call it a jet, and you have missing energy here too. Okay, yes, you have a lepton, but you can miss it. Okay. So, but it turns out that this you can go through a similar argument of my scaling. So this is start out its life at 350. You have to scale it to 4 TeV, right? So basically, and that's the biggest factor, and so on. But this actually gets down to femtobarn level too, with in this regime of phase space. Okay. So. What else I can do? Yeah. So there are many. So maybe we can do one more thing. Yeah. So that's the Gluino search. Perhaps. So let's do another example. Let's do Chagino search. Okay. So that's the partner of W. Okay. So it's produced like this. Okay, it's produced like this, and well, if it's LSP, if the we know is already LSP, for example, and then it's dark matter search, which we'll hopefully we'll get to later. But let's say that it's not LSP. Okay, now there's a LSP on top of it, and then there's a W, and then there's a W. Okay. So it's W plus W minus plus missing energy. Okay? And the current limit on this guy is M chi plus minus is around the 500 GeV. Okay, and the cross section of chi plus and chi minus at this energy is about a picobar. Okay, so you already see there's a difference. Okay, here that this is a much bigger rate. Okay, then this is a bigger rate than this guy. Okay, which is not surprising because we're talking about much smaller mass. The rate reach is much smaller. Okay, and because yeah, well we'll see. So the major background of this is just WW. Okay, the main background of standard model of this is just WW. Okay, why? Well, you have to think what these guys decays to. Okay, so if both W goes to jets, both W goes to quarks. If both W goes, I have basically two soft jets here, two soft jets over there, with some missing energy. Okay, that channel is almost hopeless. Okay, so the jets is not very hard. Okay, the jets is around the energy is around the W mass, so the jets are not very hard. So it's not very useful. Typically it's not that useful. Okay, there's still some reach with that channel. A more useful channel to think about is that both of these goes to leptons. You pay a branching ratio, but the leptons are cleaner. Okay, so another way of saying this is that if these guys both goes to jets, then your background is not just this one. Okay, you have QCD production plus missing energy. Then your background is jets plus missing energy. That background is big. Okay, but if you both goes to leptons, and then at least in this case, and this is L nu, this is L nu. Okay. So WW you start out is 100 picobar. Okay, but that's on threshold, and the rate once you do the PDF down to a TeV. Okay, the PDF central mass energy is a TeV. Okay, for this guy. Down to a TeV, it gave you a factor of 10 to the minus 2, basically taking that 100 picobar down to a picobar level. So that's why the limit is around 500 GeV. Okay. Okay, maybe I should just stop here. So tomorrow, so next time we can, well, I think I'm going to probably talk about Higgs coupling measurement at the LHC, perhaps also at the Higgs factories, and maybe after that we'll spend another lecture talking about dark matter, or we can switch the order. Depends on the Okay, let's stop here. Yeah.
Any questions before we go for coffee?
Yeah.
So you said for each particle you have a factor of 10 to the minus 2 to 10 to the minus 3.
Yeah.
When do you have a factor of 10 to the minus 2 and when 10 to the minus 3? What's influencing that?
So you pay a coupling constant right here, and you pay additional there is additional particle. You also have some phase space suppression, right? You add one more particle, you have phase space suppression, but then sometimes you have singularities. Right, if you radiate a jet, from a quark, and then you can have some enhancement, because if the jet and the gluon and the quark are close to each other, then there's some enhancement. So this is only meant to be a very rough guide. Okay, there's I can certainly imagine the case where there's no suppression at all, and there are cases where the suppression is more than this. But roughly speaking, if you add another hard particle that's well separated from others, it's around this factor, I think. Yeah.
Where do you get the cut for this diamond? Is it by the chip algorithm itself?
Yeah. So you form yes. What you actually do is in experiment is you cluster and you form jets, and you make a cut on the jet PT. So this is just the simplest cut you can impose on the jets, right? You can also impose other things on the jet, but this is just to guide your eyes, basically just to say if you have hard jets like this, what the cross section is, right? So if I don't have this cut, the cross section diverges. Okay, so of course the biggest cross section is you just have some very soft the hadronic stuff. Yeah.